All right, welcome to section 3.4, measures of position and outliers. So when we talk about the measures of position, we're talking about where an observation lies in its data set, and this allows us to compare apples to oranges. So the goal of this part is we are going to be comparing observations from different data sets. That's that, comparing apples to oranges. And to do that, we compare the positions of the observations in their corresponding data sets. And we do this using a z-score mainly, and then we can also do it using percentiles. All right, so let's talk about what the z-score is. We could use the z-score, and the z-score gives us the distance from the mean in terms of standard deviations. And we're going to be using z-scores a lot in Chapter 7 when we're doing our inferential statistics. But for now, we're using it as a position of an observation. All right, so the z-score is the distance from the mean in terms of the standard deviation. All right, so let's write out our z-score. Z-score is the distance from the mean, so for distance we use subtraction. So there's our observation x minus the mean. We'll use population. And in terms of standard deviations, we essentially want to know how many standard deviations is that mean. So we're going to divide by the standard deviations. All right, so this was for our population. If we had a sample, then we would use our sample notation. So x bar is for the mean, and then s is the standard deviation. All right, so if we were to make a histogram of all the z-scores, so all the observations, we calculate their z-score, and then we plot them and make a histogram. The distribution of z-scores It has mean 0 and standard deviation 1. All right, and also, that's a 1. Also notice when we calculate the z-score, units are in the numerator. So we know mean has units and standard deviation has units. So when we divide by them, the units cancel. So the z-score is unitless. The z-score is unitless. Let's write that out. We'll just say that. The z-score is also unitless. All right. So let's look at an example. Or I'll kind of give a quick example before we look at this word example. When we're talking about comparing apples and oranges, let's talk about heights, and this is what our next example is. But I like to use the example of my husband and I. My husband is 5'10", and I am also 5'10". So we're the same height. We're the same height. But 5'10" for a man, for a male, is an average height, and 5'10" for a woman or a female is above average. So if we were comparing our heights, we wouldn't say that we're the same height and I'm average height and he's average height. I am relatively taller because I am above average and my husband is above average. Excuse me, my husband is average height. So that's what a z-score can do. A z-score, I would have a higher z-score because I'm above average, and my husband would have a lower z-score, and that would tell us that I am relatively taller. So let's look at an example with actual numbers. We're looking at basketball teams. We have that the mean height of males 20 years and older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females is 63.7 inches with a standard deviation of 2.7. And we want to know who is relatively taller. Is it Kevin Garnett, whose height is 83 inches, or Candace Parker, whose height is 76 inches? So Kevin Garnett is definitely taller, but we want to know who is relatively taller. So who's essentially more above average, right? Kevin Garnett and Candace Parker, they're both basketball players, so they're both very tall. All right, so when we see this word relatively taller, we know who's taller, but relatively taller means we are talking about a z-score. We're going to be comparing z-scores. Whoever has the bigger z-score is farther away from the mean. They're relatively taller. Okay, so let's calculate each of the z-scores and then compare the z-scores. So here's Kevin. We'll do Kevin first. So Kevin's z-score, it's the observation minus the mean height for men. Let's see, that 69.1. And then we're going to divide by the standard deviation. So this is going to tell us how many standard deviations above the mean Kevin is. All right, so again, that's your formula for your z-score in case you're wondering where that's coming from. All right, and if we do this calculation, we do the numerator first by order of operations. We should be getting a 4.96. So again, this means no units, that he is 4.96 standard deviations above the mean height. All right, let's look at Candace's z-score. All right, so again, it's the observation, her height minus the mean height of females, over the standard deviation. So we get 4.56 when we put that in our calculators. So Candace is 4.56 standard deviations above the average height for females. All right, so we can see who's relatively taller just on this information, right? We see that this z-score for Kevin, is higher, so that means he's taller. All right, and we can sketch out a quick distribution. So again, remember, we can make a distribution of all the z-scores. And we would have a mean of 0 and a standard deviation of 1. So I'll just write z right here. This is our z distribution. And we just got that Kevin was like 4.96, almost 5 standard deviations above the mean. So he's very tall. And Candace is also very tall, but she's 4.56 standard deviations. So Candace is right here. So who's relatively taller? Well, whoever's more to the right. Because when we go to the right, that means bigger. So Kevin is relatively taller. Because he has a bigger z-score. All right, so more to the right means bigger, means taller. Okay, so we use z-scores to determine where an observation is in its data set, and it allows us to compare different data sets, just like that example. We could compare female heights to male heights. All right, we can also use percentiles. I know when I take my children to the doctor's office for their well-being visits, they check their height and they check their weight, and they give me the percentiles. I actually currently have a very large baby, and he's in the 99th percentile for weight. This means that he is bigger than 99% of all babies. We're also given percentiles when we get our SAT scores. Sometimes we get that we're in the 80th percentile for our SAT scores. That means we did better than 80% of students taking the SATs. Okay, so the technical definition, kth percentile, we use P sub k, of a set of data is a value such that k% of the observations are less than or equal to the value. All right, so we have some examples here. We have P sub 99. We would call that the 99th percentile. So the 99th percentile right there, it means a couple of things. It means we're in the top 1%. And it also means that we're more than 99% of the data. So 99% of the data would be below that value. Okay, so those are your percentiles. And then a percentile we're really going to focus on are quartiles. And quartiles, we see the word quarter. And quarter is 25%. All right, so we're going to think of quarters. So 1/4, 25 cents. So we're going to break up our data set into 4 equal parts. All right, and in terms of our percentile notation, let's see, well, the bottom would be P sub 0. That's 0 percentile. The top would be P100. And then we're going to physically divide up our set. So this would be P sub 25, P sub 50, P sub 75. But we're going to call these quartiles. So we're going to use a Q. The 20th percentile we're going to call Q1. The 50th percentile we're going to call Q2. And the 75th we're going to call Q3. We also have another name for Q2 because it's the physical middle, right? 50% is below, 50% is above. P sub 50, quartile 2 is also the median. So how we're getting these quartiles is really similar to how we found the median. We put the data in ascending order, and then we find the physical middle. And this also gives us the following property, since we know medians are resistant to extreme values, and because quartiles are essentially calculated the same way, quartiles are also resistant. Which is important because when we have extreme values in our data set, we like to use numerical summaries that are resistant. So quartiles are resistant. All right, so let's look at an example using our quartiles. So we have these students. They collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed was 25 miles per hour. So that means all the cars went 25 miles per hour, right? Well, let's see. The recorded speed of 14 randomly selected vehicles is given below. Oops, we kind of failed on that, right? Not too many people went 25 miles per hour. All right, so as I'm looking at this data, I'm also noticing that it's already in ascending order, which is awesome. And so we're going to find and interpret the quartiles for speed in the construction zone. All right, well, quartiles are like medians. So the very first step is to put everything in ascending order, and it's already in order. So I would make a note of that. So notice that this is in order already. Oh, come on. Okay, so to find the median, we can go from the outside and work our way in since it's a relatively small data set. It's an even number 2, so to find the middle, we could divide 14 by 2, so that's 7, and we know the median would be the 7th and the 8th entry. So the median would be the mean of the 7th and the 8th entry, or the midpoint between 32 and 33. So the midpoint would be 32.5. That's your median or your second quartile. To find the first quartile, we would take the first chunk of data and divide it into 2. And now there's 7 on this side, so we know that it's going to be the 1, 2, 3, the 4th entry based on our formulas from before. And then likewise in the second set of data, 1, 2, 3, 4, that 38 is right in the middle. Okay, so we took our data set, we divided it in half, and then we divided each half in half, and that's how we're going to get our quartiles. All right, so our first quartile is that 28, but we still have units, and this is in miles per hour. So the first quartile is 28 miles per hour. Central tendency always has units. And again, if you wanted to be thorough, this is the same as the 25th percentile. And now we want to interpret this. So again, this is a percentile, so it means 25% of the data is less than this 28. So we can write just that, 25% of drivers drove, we'll say drove slower than 28 miles per hour. And then we can do the flip side. So if 25% drove slower than 28 miles per hour, that means 75% drove faster, because that's how percentiles work. We kind of get a 2 for 1. All right. And so we can repeat this for the next 2. Really similar. Your next quartile, we already said, was 32.5. We're going to remember our units. And then the interpretation of the median or the quartile 2, again, remember it's a percentile. So we could say that 50% of the drivers drove slower. And 50% drove faster. Than 32.5 miles per hour. And then finally, your last quartile was 38. So we would say the third quartile, Q3, was 38 miles per hour. Again, that's the same as the 75th percentile. So that's how we interpret it. So 75% of drivers drove slower. And 25% of drivers drove faster than 38 miles per hour. All right. We can also use our calculator to help us calculate quartiles. This was a relatively small data set, so we could do it by hand. But again, if we had a data set of like 100, this would be hard to calculate by hand, or at least tedious. So to use our calculator, again, we would just go to one var stats after we put our data into a list, of course. And if you scroll all the way at the bottom, you see Q1, median, Q3. All right, so we can always put our data set into a list and use one var stats to get our quartiles. All right, so we can also use the quartiles to measure dispersion. This is handy because quartiles are resistant. So if we have a data set that has extreme values, now we have a measure of dispersion that is resistant. That would be appropriate for a data set with extreme values. And then just to remind you, the standard deviation uses the mean. And the mean is not resistant. So the standard deviation is not resistant. All right. So what that dispersion is called, measured dispersion of, it's called the interquartile range, or IQR, and the IQR is resistant. All right, and what the IQR is, not the formula, but what it is, it's essentially the range, or it's exactly the range of the middle 50% of your data. Okay, and so the range of the middle 50%, well, we know the range is a difference. So the IQR, it's the third quartile minus the first quartile. So in our previous example, the third quartile was 38, the first quartile was 28, and so the IQR was 10 miles per hour. All right, and then let's draw a little picture. Pictures always help. All right, so the IQR is this middle 50% right here. This is your IQR. Okay. So we like this. It's a resistant way to measure the dispersion. It also helps us determine if something's an extreme value. So right now we're just saying extreme value, but we have no way, it's based on our opinion, and that's never good in statistics. We want to be able to measure everything. So we can use the IQR to actually tell us when a data set has outliers or extreme values. Again, outliers can actually be caused by chance, because even though it has a low probability of occurring, it can still occur. So outliers can occur by chance or by an error, such as data entry. So let's see how we are going to calculate this. So we can use the IQR to calculate fences. Anything outside the fence is an outlier. Okay, so kind of a visual for this. Let's bring back our little chart. So this is our data set, minimum and maximum values are shown right there. And then we have our median, or Q2, our Q1, and our Q3. So what we can do with the IQR is we can establish fences. All right, and so we calculate the fences. Let's say one fence ends up being right here, and then another fence ends up being calculated, the value ends up being right there. And anything outside the fences would be considered an outlier. So notice on this side how I constructed it. This fence, all of our data is inside our red fence. But over here we have one data hanging out. So this would be an outlier, because it's outside our fence. All right, so let's see how we calculate the fences. We have two fences, our lower fence and our upper fence. And the formulas are very similar. All right, so here we start with Q1 for our lower fence, and we subtract 1.5 times the IQR. And that's going to give us that lower fence. We also have our upper fence. And we start with Q3, and we're going to add a little. We're going to add the same thing, 1.5 times the IQR, to get the upper fence. Okay, so those are our formulas. And again, anything that lies outside the lower fences and the upper fence is going to be considered an outlier. So now we want to know, are there any outliers in the previous example? So when you're asked to see if there's outliers, you should think to yourself, I have to construct my fences. Okay, let me rewrite all the information since it's on the other page. Q1 is 28. Q3 was 38. And then the IQR is 10. So your lower fence is Q1 minus 1.5 times the IQR. Remember multiplication first. So it's going to be 28 minus 15, it's 13. So anything in our data set less than 13 is an outlier. Let's look at our upper fence. Now we start with Q3. We add 1.5 times the IQR. So 38 plus 15 is 53. So anything bigger than 53 is considered an outlier. So I'll give you some time. Go check the data set. And again, anything less than 13 and anything more than 53 is an outlier. So what are you guys finding? Do we have any outliers? No, we don't. All right, so we're going to conclude no outliers from that previous example. Okay, excellent. So now we have an example for you guys to do on your own. So you guys can pause the video right now and go ahead and do this example. We are looking at the hemoglobin for 20 randomly selected cats, right? And notice we have to, in the very first one, we have to compute the z-score. For the z-score, you need the mean and you need the standard deviation, and those aren't given. So what do you think your first step should be? That's right. You guys are going to want to do a 1-var stats to get the mean and the standard deviation. Okay, so go ahead and pause this, and then I will write out the solution, and then you can come back and push play to see how you guys did. All right, let's see how you guys did. So you put your data into a list and you did your 1-var stats, and here's your mean and your standard deviation. And again, that was your first step because we wanted to compute the z-score next. So Carrot, my former cat, this was her hemoglobin. And we took the observation minus the mean, divided out by the standard deviation, and that gives us our z-score. And notice it's negative. That's perfectly okay. That just means that Carrot was below the mean. So that negative just means that she was below the mean of the hemoglobin. All right, so negative just means to the left. All right, so perfectly acceptable to have a negative z-score. Don't forget the negative. The negative part is important. Quartiles you also can do with your 1-var stats. You could scroll all the way down to the bottom. Remember, the Q2 is the same as median. And you guys want to include your units on that. Z-score is unitless, but quartiles is a measure of central tendencies. So we're going to want our units. You did your IQR. That's our formula, Q3 minus Q1. And there are your units again. And the interpretation is it's, again, the range of the middle 50% of the data. Finally, with the IQR, we can determine our lower and our upper fences. So that's what we did on our next step using our formulas. And we can use the upper and lower fences to determine if there's any outliers. So again, anything less than the lower fence, anything more than the upper fence is an outlier. And going back to the original data set, we have that 5.7 is less than the lower fence, so that's your outlier.